Okay.
Is that a good angle?
Yeah. Yes, you can see his face and the PowerPoint.
Yeah.
Devious amount of energy.
Can everybody see the thing? No, I'm not in anybody's way.
I think we're good.
Alright, ready? Hello. Alright guys, my name's not Cameron McKinney. As you might know, he's stuck at work right now, so I'm going to be giving the first part of this class.
Question.
Yes?
Can you move the podium at all?
That's what I was asking. Is like, does anyone have a...
Thank you.
So basically this class is on how to do research. So research takes many forms. We're not just talking about how to do original published research. We're talking about everything from breaking a manual down and figuring out how a board works or how a motor works, to taking an algorithm and implementing it, all those steps that you need to get from not knowing anything or a small percentage of what you need to know to knowing enough to implement these really complex solutions to these really hard problems. So to give you a little bit of background, this is basically a definition of research, which tells us that research is basically you're going through and trying to systematically figure out a solution to a problem. In our case, as engineers, computer scientists, I don't know if there's anyone who's not in that particular realm in here, but in general, you're trying to solve a problem. So we have these complex problems. From the autonomous side, we have to make a car drive itself around a track. Now, it sounds simple to say, but there's a lot of pieces and facets of that problem that cause us to have to think very creatively and figure out solutions to these things. It's also true on the driven side as well. Things like the dual motor cart will require significant time and effort to figure out how to make them work, and it's very important that we have the skills to do that. So the relation to DVT, as I mentioned, was in our cases are the dual motor cart. So the dual rear motor cart is going to be a torque vectored cart, which basically means that the two rear wheels will spin at different speeds depending on how the cart is turning, and that will increase handling and such. We also have autonomous research, which does everything from mapping to path planning to controlling the cart, creating a low-level safety system to make sure the cart doesn't run anybody over. There's lots of very difficult problems and very important problems to be solved. And all of this breaks down to research. So now that I've said research a bunch of times, we kind of want to talk about what that process looks like in a bit more concrete way. So in our case, we're going to start research with a problem. You have a problem that you can state very clearly, and you understand the scope of your problem. So you're trying to understand what your problem is. Not just your part of the understood problem, but your application of this problem. So, for example, if I am trying to say, my go-kart needs to be able to see what's around it in terms of mapping. What is my problem in that case? My problem is that I have to define my environment around me and figure out where I am. So I need to set a set of accuracy goals. How accurately do I need to know where I am within some sort of parameter? How much do I need? How quickly does this need to happen? What are my parameters for this problem? What knowledge gaps do I need to even understand what the problem means? Like, if it's a problem of, okay, I need to do mapping. What does mapping mean in the case of something like mapping a track? What does that look like? So you have to before you can start looking for solutions, you have to understand your problem. It's very important that you don't jump before you look, because it will end up with a bunch of solutions that don't actually solve the problem you wanted to go for. The solution phase is kind of, for us especially, because we, as people, we're in undergrad, we don't have a lot of experience, and if you do, that's awesome, but in most areas, we don't have a lot of experience with these problems. So we don't have a knowledge base to draw on that's within ourselves. So it really is important for us to go for sort of a shotgun approach to solutions. Don't get fixated. It's very important not to get fixated on a single solution, because what can happen is you find the first solution on Google, and it seems good enough. But if you look too down, there's one that was 5 times easier to understand and 3 times easier to implement. So you want to put yourself in a position where you've got a set of solutions and a set of metrics to judge them by. So how fast is it? How easy is it for me to understand? How much work am I going to have to do to implement it? As much as you can about these solutions, just like you did with the problem. It's really important that you break this down into these bite-sized pieces for the solution. So now I have a set of solutions, and I'm going to pick my best 2 or 3 solutions. My best, out of say you looked up and you found 10-ish solutions. You can narrow them down quickly with the ones that you can't understand at all, and you can kind of get yourself into a good place. And then you want to start looking at how you're going to approach the actual solution. So how is an approach different than a solution? So the approach is, there's lots of ways to use what you've learned. I guarantee you, if you read a research paper, you won't be able to exactly use what they put, more than likely. You might be able to use 80% of it or 50% of it, but you won't be able to use it exactly. So you have to figure out how you're going to use it. How am I going to take this from an algorithm on the paper, from a piece of code that I found online, to something that actually works to solve my original problem? Then once you understand that, you begin implementation. And implementation is somewhat beyond the scope of this, but implementation is equally important when you get to that point. And it will happen faster than you think. It is probably the hardest point, because now you're having to take all of that work that you did, and no matter how hard the problem is or the solution is, you're having to translate that to actual new things. So that portion of the problem is hard, but the good part is that if you put the work in up here, you understand your problem, so you know how to check to see if you did it well. You understand your solution, so you know how to check to see if you did that right. And you understand your approach, which means that, again, you understand what success. You understand what success means in the context of your solution. So instead of trying to implement something where you only half understand it and only half understand what the problem is you're trying to solve, you have a very clear idea of what you want. And trust me, implementation in code or circuits or whatever it is will be much, much easier if you understand all of these things before you start implementing. So now it becomes kind of a how thing. So that's why. That's why we do it, is how we break it down. So this is a very important part. You're going to want to define your goals. So we talked about it in the previous slide, that's defining your problem. You need to know what you're shooting for. It's important when you're defining your goals to say, why am I doing this? Why am I doing this particular way? Is there an easier problem that I could solve that ends up with the same set of solutions? Say, I have this really fancy mapping algorithm that gives me this nice 3-dimensional smooth map of the world, but all we really care about is dots on a page, because we are not trying to fly a plane in a 3-dimensional environment. We're only trying to drive in a 2-dimensional environment. Why am I picking this? How is it useful to the team? How is it useful to you in your own life? Is this the best way for me to spend my time? So this is Bloom's taxonomy. So this is basically a pyramid of how hard things are to do. So this is a way for us to break down what problems are. So if you look at basics, this is like, how do I take the derivative of an exponential function? I can look it up on YouTube. I can find tons of resources, and it's a very short, basic problem that has an algorithm that I can just apply, and it becomes very easy very quickly. Medium is something where, say, instead of having to take the derivative, I have to write a program to do Euler's method. So basically estimating your function value using the derivative. So I have to write a program, so I have to do a little more. So instead of having to just learn something and know how to use it, I now have to learn how to make something else do it. Intermediate, so we can think of intermediate as when you have to take something like a research paper you write in a class, and that you want to take some resources that you've found and support an argument that you're making. You want to support a hypothesis that you have. So this is something where you're basically trying to synthesize something new. This is something, but it's still not new, it's just something that you're pulling from other resources and trying to put together. That's probably about as far as we get in most college classes. Hard, so we talk about creating. When you're creating something new, this is when we're talking about you're taking something that has happened before and you're finding some way to improve it, and it is markedly better, and you have produced added new value to the world. So it's not just an implementation of something someone's already done. This is new to the world. Hardest, innovate, that's when you are actually taking and pushing the boundaries of science forward. We probably won't do that one in here, as you might expect.
Take those words back.
I said probably. I didn't use an absolute.
Okay.
So these things are something that you can these are questions you can ask yourself. How hard is this problem? The goal for this team is that we can have people that are independent enough to where I can hand a problem to you and you can go through these steps and understand, okay, how hard is this? Where do I need to go from here? And you can come back in a week and be far down the road on this problem without getting bogged down in the usual traps that we get bogged down in when we're given a hard problem. So that's where it becomes very important for you to plan. So when you initially get a problem, you want to make sure you understand it, and then you want to make a plan of attack on how to actually execute on solving it. So a lot of times we can get bogged down. I know that when I was a freshman, when I was given a hard problem, it's not something that I would go past the first 2 pages of Google results trying to figure it out. It's hard. You have to persevere to actually solve these hard problems, because they won't be, more than likely they're not going to be the first 2 Google searches you make. They're probably going to be a little bit further down the rabbit hole than that. And this resources will not be as easy to read as you might hope. He mentions the deadline stuff. This is something that's kind of personal, but if you work well to a deadline, or even if you don't, it might be something to look at doing. Personally setting deadlines and setting them and when you tell other people, I'm going to have this done by this time. Even if it's something where it's like totally unrelated, you just tell Ben, I'm going to have this done by whenever. And Ben's like, okay. Then you've told Ben it's going to be done, and you have some accountability to get the stuff finished. That's just it's kind of a hack, because even if you just tell your mom that you're going to have it done, it doesn't matter that they know whether you're done or not. You still have to report back to some extent. So that can kind of, if you're a procrastinator, which I'm sure that no one in here has ever procrastinated before, it's a good hack. From someone who was and is a procrastinator. Understanding potential obstacles, that's kind of hard at the beginning, because you're at the very beginning, so you're trying to understand the obstacles, but thinking through the problem and thinking what's going to be hard can help you not to be surprised by it. I think we went too far. So we talked about the Bloom's taxonomy, and he said things like YouTube. So a lot of times, the most important thing that we can do is break our problem down. So these fundamental research things are, say I have a hard problem, and I've been given, let's say we're at stage 4 or so, and we've been given a paper and a problem. And you're asked to take this paper apart and understand the solution so that you can see whether it's a good option or not. There is probably going to be some fundamental understanding for you to pick up, because more than likely they've written something in that paper that you don't understand, whether that's mathematical or some physical thing that you don't understand, or some programming thing or some electronics thing you don't understand. There will be some basic filling of the gaps in. So that can be a good first pass at a paper, is this section doesn't make sense because I don't know what this word is and this word is and this word is. So if I can fill in those gaps, it can really help you get further down the road with this stuff. It's a really good idea when you're looking for stuff like that, once you've gotten that initial idea of what you don't know, it's a good idea to go and kind of batch pull a bunch of stuff at once. So if you go and search for a bunch of resources, so say you find a YouTube video, save it. Say you find a blog post or a paper, save it. And do this until you feel like you have a good sampling of like the basic resources on this stuff. And then you can start looking through them, and you don't have to feel like you're attached to the first resource. So it's not working for you, you go to the next one. So the other thing, one of the things we can talk about is that sometimes research is bad. Sometimes the tutorials are not good. Sometimes it just doesn't work for you. And it's important to understand that you can move past that. I can tell you that published research is not as consistently good as we would hope it to be.
Yeah, they suck at writing.
That's the problem. There are some papers where you get down to the meat of it, and 90% of it is the same as the paper that they cited, and they've added one small improvement to it. So you would have been better off reading the original paper. So it's okay if you don't understand something or if it's something where it doesn't make sense to you. And it's not a good way for you to learn this basics. When you get to papers, a lot of times we have to identify good and bad papers because we expect, it's a peer-reviewed paper. It's going to be a good resource. That's what we were told in Comp 1 or Comp 2. That's what they told us is, it's peer-reviewed. It's great. Unfortunately, that's not true. So you have to be discriminating when you read these things to kind of figure out what fits you. So, and this takes time. As you can tell, this is not a short process for these things. And it takes a good amount of effort. But at the same time, because it's a hard problem, it's going to take effort. We already talked about finding the solutions. So this is about narrowing your problem and your solution down. So narrowing is an important part, but it happens when you're sure, when you're happy with what you've hashed out. We haven't talked at all about collaboration in this, but collaboration is an important part of this. When you get back to the point where you're picking your solution, you should definitely talk to people. You should definitely give people a rundown and say, I have these three, and this seems good and this seems good. Maybe they have some experience with it. Whatever, you can explain it, and trust me, when you explain it to them, you'll catch things that you're like, wait, but that doesn't work because, it will make a huge difference in your ability to narrow things down and figure out where to place your time. Once you've narrowed them down, you can go into implementation very confidently and without looking back at what you've done and say, I could have done it that way. It might have been better if I've done this. You can be confident that this is, by your estimation, the best solution that you can come up with. And that's the most we can ask for. Anyone can ask for. So I included this as an example of good research. You may not be able to read this. But this is a paper about SLAM algorithms in autonomous underwater vehicles. But yeah, it's a real hard problem actually because of underwater. It's a really terrible environment to deal with. But this is what it's going to be distilled into. This is what your creation would be distilled into. That is a big one. So this is a list of questions. I don't want to go through them one by one because I don't think it's important, but it is good to have questions to ask yourself. So this is kind of like we in programming it's called rubber ducking. This is something this is an alternate version of rubber ducking where you can ask questions of yourself and say, explain it. So you can kind of recreate the same effect as when you have another person in the room and say, because you're explaining it, and it's important that it's out loud. Also, that's why they have a rubber duck, because they tell the rubber duck how it works. So this kind of stuff can help you move into that, especially when you feel stuck. If you've ever had a problem from a teacher that's told you to solve this and they don't give you enough resources or whatever, and you feel very stuck, this is the kind of stuff that can help you get to that, at least being able to find what you're looking for. This is a little bit deep for this. But this is something you talked about. So we talked about papers not always being great. A way to avoid reading bad papers is to read the abstract or the introduction, depending on what kind of paper it is, and the conclusions that they cover. So a lot of times, if you look in the conclusion section, it won't be technical. It'll be telling you what they accomplished. And if it doesn't sound very impressive, what they've accomplished, and it's talking a lot about building on someone else's solution, you should probably pull the paper that they're referencing and look at that one instead. But you can kind of tell, when you read an abstract, you're like, it's supposed to tell you what the paper's about. In your introduction, you can kind of see where the author's going with what they're doing. So it can take a long time to read a research paper, so save yourself some time. Read the abstract, introduction first, and then read the conclusion. And then determine whether it's something I want to pursue. Do I want to keep going? This is talking again about fundamentals. So one of the things diving into this type of research can help you do is pick up on fundamentals. We've been talking a lot about papers, but in the case of something like, we have a problem where we need to figure out how to use a certain motor controller for our cart. So you can dive into this and start reading the literature on the motor controller, and this will teach you all about how people do embedded systems for motor controllers, how the motor controller itself works, how it's wired. So you can learn a huge amount of fundamental stuff by diving into a hard problem, as long as you approach it from the perspective of, this is a mechanism for me to learn stuff, instead of, I need to solve this problem as fast as I can. Because in general, what we want is you to pick up as much knowledge as you can, because it'll make you more valuable, not only to us, it'll make you more valuable in your jobs in the future, make you more valuable in your classes. It will make a big difference. So
It makes you more valuable to yourself. That's the self-actualization.
So I want to, let's see. So to give you some context of what we're going to be doing next week and what we're going to be continuing to do.
This was, wanted to give out homework as well.
Yeah, there's homework on the left side.
Okay.
So basically what we're going to be doing, so now that I've talked about it, we're going to do it together as a group. So what we're going to do is we're going to pick some papers / manuals / whatever resource it is that is applicable to your particular area. And we're going to go through the process of picking it apart and understanding each piece of the problem as a class. And at the end, we'll all present on it so that everyone learns a whole lot about a whole lot of different things. Because if you can teach it, then you actually know it. That's the most important thing. This is going to help you learn some new stuff. It's a good opportunity to do it. There's obviously no grade, because I'm not going to give you a grade. But I guarantee you this will help grades in your other classes going in the future. And this will help you to be an effective researcher. So what we're going to be looking for is, there are some topics listed here that give you kind of general topic areas to go into. What we're going to be looking for is you to bring between 2 and 4 papers next week that you think you want to look at. So this is important that you want to be interested in the area that you pick, because this is going to be the one we're going to pick apart for the next month or so.
Does it have to be from one of each category, or can it be from the same category?
What do you mean?
It can be from the same category.
Yeah. If you have an idea, that's perfectly fine. This is just to give people kind of somewhere to look. So we want you to bring 2. The reason I want you to bring more than 1 is because we want to sit down at the first part and figure out, is it reasonable for me to learn this in 4 weeks? Because if you sit down and bring something that's a higher level math paper that you have only taken calculus, or you haven't even taken calculus yet, it might not be the best one to start with, because you're missing so many fundamentals. So these are some interesting. We'll be posting this, so you don't have to keep track of these categories. But the most important thing is picking out something that you think is interesting, so that you're willing to stick with it to some extent. And we'll try and help you guys narrow into areas if you're not sure. So you can talk to me or Ben or whatever if you're like, I don't know what I want to do. We can find something, I promise, that you want to do. But I wanted to wrap this up. The purpose of this is that Cameron and I he's graduated and I'm graduating in December. And this is the stuff that I wish I had known when I was a freshman. I wish I had known how to solve problems this way and how to do research this way. I didn't really get to this point until last fall when I did my senior project. And if you're doing it as a sophomore, junior, even if you're doing it as a first semester senior, you're ahead of curve on this stuff. This can really help you in your classes, because if you take this and apply it to your higher level engineering classes, they will have a lot of these problems where diving into it can really help you move past that kind of shallow knowledge that we get in classes and actually understand the underlying material that's very important for you moving out in your career. And also, as someone who's done a fair bit of work in the engineering field, this is the stuff that you want. If you want to work in an interesting area, this is what you're going to be doing. You're going to be taking problems, you're going to be given a problem, or you're going to have to come up with problems, and you're going to be taking them apart, and you're going to have to come up with solutions that work within all kinds of parameters and all kinds of restrictions. So that's what you're going to do if you're in engineering, if you're in computer science. Even if you're not, probably going to still look a lot like this, just will be with different stuff. So that's it. If you guys have any questions, I'm ready to take questions. What you got, Ben?
Where do we go to find research papers?
So that's a really good question. So it depends on what you're looking for. So say you're a mechanical engineer. If you're looking for a paper, ASME, American Society of Mechanical Engineers, it's a great place to look. If you're electrical, computer science, if you're interested in autonomous technologies, IEEE is a great place to look. Also, Google. Google Scholar is actually really good.
I was about to ask if that was if that was credible or not.
Yeah, I mean, what you want to do, so credible, okay, so here's something we have, so credible research in the engineering field means probably like not mind control or like it's easier for us because we're not trying to find credible like a journalist is trying to find credible. We're trying to find useful, right? So that's your highest criteria. It's not just that so if it's a published paper, it's got some usefulness, at least, to it. I'm also going to encourage you to stay, conference papers are a good place to start because they tend to be a little shorter. Journal papers tend to be like 12, 15 pages, and that can be a lot, because a lot of it's experimentation and it can be kind of a whole other thing, understanding their experimental procedure. If you're looking at something like, let's say, your emergency system, there might not be a paper on that, like a direct paper. So come up with a list of things, of resources, and stuff like that we can kind of define out for you a little more.
I would say for like the specific like dash design, like elite and battery pack design, I would say for presenting on that, compile like at least 10 like sources of where it's been done before and where you've seen it online.
Because that's another problem. So in our case, we're talking out of the paper because in a lot of cases we'll be talking about taking the paper once you've gotten the problem and you've gotten the solution you want to do, and now I have to figure out how to actually make it work. But this part is actually something we didn't talk about a lot. This part is coming up with the problem. What problem do you want to solve? What problem do you think is interesting? And these are just some examples of some categories that we have to solve. How do we make a redundant perception system? How do we use cameras for perception and figure out where things are in relation to us just using a camera? I would stay away probably from stuff like mounting solutions for this particular class, unless you're talking about like damped solutions where you're trying to figure out like how to reduce vibrations to the like highest level possible. Try and find something that's a sufficiently like out there problem that you can work on it as well. So it's a hard balance. Get a balance between I can get to it and it's not so easy that I could finish it in a CAD drawing tonight. Any other questions? Comments? Concerns? Alright. Who is?